The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
I didn't quite get a chance to tell you a few things about Photosystem 2 last time, so I'm going to go ahead and finish up with that now before going on to the Cardiolite story. And Photosystem 2 shares quite a lot in common with Photosystem 1, but there are a few major differences. Photosystem 2 is the first link in the chain of photosynthesis. It's really where all photosynthesis starts out on Earth. And as such, it's an extraordinarily important enzyme, this Photosystem 2. But it's such a large and complicated enzyme, and it's also a membrane enzyme, as I mentioned last time. These are difficult to isolate and purify and crystallize so that you can study their structures. And so it was only in the last couple of years that Photosystem 2 was actually crystallographically characterized. So there's really a lot of very recent science that's relevant to today's presentation on Photosystem 2. And as you go through and read about it, you're going to learn about the molecules that harvest the light, and you're going to learn about where the electron goes and where the hole goes when light is absorbed by this amazing system. Here's a close-up of part of the system called the reaction center. For obvious reasons, this is where the reactions take place that are so integral to photosynthesis. Namely, we have up here at the top a manganese-containing cluster, the structure of which is still a little bit ill-defined. As you can imagine, with a macromolecule of this size, it's difficult to say exactly where just each and every atom is in the structure. So there's still some details of the structure of the manganese cluster here that aren't known. But nonetheless, this is where two water molecules must be brought in and coordinated, and ultimately where water, which is not a good reducing agent, serves as a source of electrons in this system. And what happens is this special pair of chlorophyll molecules at the heart of the reaction center absorbs a photon and goes into an excited state. And the electron is able to travel down through a series of pigment molecules, and it gets down onto this plastoquinone A, and it's able to jump over onto the plastoquinone B. And plastoquinone B then can dissociate from the reaction center and carry that electron on to the next link in the chain in photosynthesis. And at the same time, the hole is stuck back over here, and it ends up accepting an electron by oxidation of a reduced tyrosine moiety here. This tyrosine has a phenoxy residue. It's it's connected to the amino acid polypeptide backbone of this protein. And it's positioned right here between the manganese cluster and the special pair, so that once the electron is shuttled away down this redox cascade pathway, it is juxtaposed with this reduced tyrosine, which is getting its electrons from the water that's coordinated to the manganese complex, and somehow those two water molecules, after giving up their 4 electrons, become O2. And O2 gas bubbles out, and that's the source of the oxygen that we breathe on this planet. So this is, needless to say, a very important enzyme to understand. And I won't have time to go through an exploration of the structure today, but I will lead you into it by showing you this picture. And in this picture, the sort of gray background that's mapped out here on the outside, it represents this polypeptide chain, all the many amino acids that are linked together to form the protein container of Photosystem 2. And you can see that it looks like a dimeric structure where you have one reaction center over here. Here's a special pair located there. And then all embedded throughout this protein, you find many cofactors, which are like porphyrins, but they contain magnesium, and they're these chlorophyll units. And then also shown in sort of an orange color here, you see these long straight molecules. These are polyenes. These are carotenoid molecules, organic molecules that have strings of double bonds adjacent to one another so that they can conduct electricity and conduct energy. And this is a really key feature of this, because the point that's being made here is that the photosynthesis doesn't wait until a photon actually comes in and impinges right there on the special pair. A photon can come in anywhere on this big molecule, or on these light harvesting proteins shown at top and at bottom that come up and dock next to photosystem 2. And these light harvesting proteins are also just chock full of light absorbing chromophores, chlorophylls, and carotenoid molecules. And if a photon comes in and excites one of these molecules over here, the proton has a mechanism for transmitting the energy over to the special pair so that water can be oxidized to O2. So it's really quite a tremendous assembly of different kinds of molecules to perform function. And if you go on and take 503, for example, and then 504, you will learn about the rules that govern electron transfer between molecules and also in proteins. And let's see. So finally, on this subject, I will show you here a view of this reaction center. And this is just a close-up to show you that these water molecules indeed must get in here. There's also a calcium ion present at this active site where the water molecules are being oxidized and converted into dioxygen. And here's that tyrosine residue shown in more detail that's very important for the hopping of the electron from water to the tyrosine, and then over here after the hole has been generated through excitation of the special pair of chlorophyll molecules. So that brings me to the end of my discussion of 6 metalloenzyme systems that had quite a bit in common in terms of the ligands that are used to bind metals. We talked about the heme last time and its employment of the porphyrin ligand in this regard. But then you should also remember that sometimes you see clusters tacked into protein molecules as cofactors. We saw last time some Fe4, S4 clusters, and here a manganese cluster. So that inorganic and organic molecules are all working together in a beautiful synergy to enable photosynthesis. And having said that, I would like to now go on to my final topic, which has to do with the role that metals can play in medicine. So last time was metals in biology. Now we'll talk about metals in medicine. And there are different ways that metals can be used in medicine. For example, there are molecules like cisplatin that are used in therapeutic methods for treating cancer. Alternatively, metals can be used in a diagnostic manner. And that's what I'll be talking about here today. And so what I did for today was I went directly to a couple of the PhD theses that are in the MIT Digital Archive by two students who worked in the chemistry department here and earned their PhD theses doing the chemistry of technetium. Now, I like technetium for a lot of reasons. One, it's a neighbor element to molybdenum in the periodic table. Number 2, it's named after MIT, so that's wonderful. Number 3, it's actually technetium is unique as an example right in the center of the periodic table as a man-made element, and it's been known for quite some time. And I'm going to tell you a little bit about how technetium chemistry has evolved in the MIT chemistry department. And so this first thesis is a 1983 thesis of a fellow by the name of Mike Abrams. A very smart graduate student who was given a very difficult research problem indeed for his PhD thesis. And that had to do with preparing compounds directly from the pertechnetate ion. And pertechnetate is the ion TCO4-. Okay? Let's scroll down. And if you look through this, you're going to see why Mike Abrams needed to prepare compounds directly from the pertechnetate ion. And it has to do with the idea that there's an isotope of technetium, an isotope known as technetium-99m, M for metastable, that has a 6-hour half-life. And in that 6-hour time window, that is the half-life of technetium-99m, it is dropping from a nuclear excited state into a nuclear ground state, and I'll talk more about that in a moment. But as the nuclear excited state relaxes to the ground state, this nucleus emits a single gamma photon at about 140 kiloelectron volts. And so that single gamma photon, high energy photon that comes out when this nucleus decays from 99M to regular technetium-99, which has a much longer half-life on the order of 10 to the 5th years, is what's useful in a branch of medicine known as nuclear medicine. So radiologists will be interested in this, and as you'll see, cardiologists will be interested in this as well. And so because of this, gamma camera images can be obtained at high resolution to image organs that have taken up this radioisotope. And okay, and let's point out also here that the chemical form of technetium obtained from the generator that creates it is the pertechnetate ion. So all radiopharmaceuticals have to be prepared from TCO4 minus, because that's what you get. Okay, so molybdenum-99 is a product of nuclear fission, and so when people are using nuclear reactors to make energy, they're accumulating a lot of molybdenum-99, and molybdenum-99 is an unstable isotope of molybdenum. And so it's right to the left of technetium in the periodic table, and molybdenum-99 itself undergoes a beta decay in which a neutron turns into a proton and electron. And that beta decay converts molybdenum-99 into this metastable isotope of technetium. So what happens is that every morning at the hospital, the molybdenum-99 has been coated as MoO4 onto an alumina column, and it's undergoing its own beta decay. And when that's done, you have now got pertechnetate on the column, and you can elute that in very dilute solution, in saline solution, isotonic saline solution, and you then have a very small amount of time to do chemistry with it before you put it in the body. And so therefore, Mike Abrams was given the problem, and I'll tell you about the professors involved in this in a little bit, but was given the problem of finding a way to take an extremely dilute solution on the order of 10 to the minus 9th molar solution in saline and do a quantitative reaction from pertechnetate to make something that would go and localize in an organ that you want to image to find out about the patient's health. That's a tall order, but that didn't stop them from looking into this. Okay, and in fact, I included this page in part because Mike Abrams has some nice statements here. He says, this is the reason we carried out this research is to gain a better understanding of what kinds of coordination complexes can be prepared directly from TCO4 minus, with the hope that such information might lead to the development of new radiopharmaceutical agents and or to a better understanding of the agents already in clinical use. Okay, this thesis was written in 1983, well, let me not get ahead of myself here. Okay, and let me just show you here one of the first technetium complexes that Mike Abrams was able to prepare. And this is a technetium hexakis thiourea species. Okay, so you'll see that he's got this pertechnetate and he's able to convert it into molecules that are octahedral at technetium. And in fact, most of the applications of technetium in nuclear medicine do involve octahedral 6-coordinate technetium, you know, hearkening back to what we can understand based on the efforts and achievements of Alfred Werner. So here's the octahedron, pretty soon, you know, going to go into a patient's body. Here he's chosen to use sulfur donor ligands, these thiourea ligands, in making this, and he also made molecules in which phosphines and phosphites were able to bind to technetium. And later, as you'll see, he also did work with isocyanides. Okay, let me rotate this one. I wonder if this works. No, let's see. All right, I'm not going to worry about rotating this. This is 90 degrees rotated. Basically, the reason I'm showing you this is that this is a nuclear magnetic resonance spectrum of a technetium-99 compound. So let me just explain that initially, when doing these studies, Mike Abrams was working mostly with technetium-99 that has a real long half-life. So then you could actually make molecules on a scale sufficient for isolation and purification. But then those methods would be translated to working with the 99M isotope. And the 99, the difference between 99 and 99M has to do with the spin of the nucleus. So we've talked about electron spin. Well, different nuclei have themselves the property of spin. And technetium-99 has a spin 1/2 nuclear spin. And then when it decays to 99M, from 99M to 99, the 99 isotope has a spin 9/2 actually. And that's the lower energy state that gives rise to this gamma photon emission. And so in the nuclear magnetic resonance spectrum, observing the phosphorus 31 nuclei that are connected to this hexakiss phosphite of technetium-1, you see that there end up being 10 lines, and that's because of the spin 9/2 ground state of the technetium-99 nucleus. So you'll see that back in the 80s we were looking at technetium-coupled phosphorus NMR spectra, as well as you saw X-ray crystallography a moment ago. So this was real nice work. And let's see, what do I have here? Okay, so after Mike had successfully synthesized some of these complexes, they started wondering, well, can we image organs with these? And the idea was that radiopharmaceuticals that had been in use prior to this time didn't really have ligands on the metal. You know, it was sort of the case that they would take the metal in whatever form they got it off of a generator and just inject it directly into the patient. And in that case, you don't have an ability to tune the properties of the metal to have it localized specifically at organs that you might want to image. And so they thought, well, you know, we're coordination chemists. Let's put ligands on there, and you can use different ligands, and then the molecule will go to different parts of the body specifically. And when we find the right ligand, we'll be able to do something useful, like image the heart. And so here they had an anesthetized dog that they had injected with a solution of one of these technetium complexes. This was a hexakiss tert-butyl isocyanide technetium-99M, and they were able to show that this stuff forms quantitatively even at the tracer levels that they're using, to 10 to the minus 9th molar, very dilute solutions. And so you don't actually get much radioactivity put into you, but because of the high energy nature of the gamma photons that come out, you can easily image them with a gamma camera, and you can reconstruct the position from which that radiation is originating, and that's what allows you to image an organ. And so here's a little schematic of the rib cage of a dog, and you can see he's telling us where the liver is, and then you're supposed to be able to see kind of a donut, which is the myocardium of the heart here, and you see it lighting up real nice right here. So right away, with one of the first complexes that they made, they found that this stuff goes shortly after injection and localizes in the heart and gives you a pretty nice image of the heart. And there are different viewpoints that you can take when you image the heart using methods like this, but this was already pretty exciting. That one of the first systems they made, these tertiary butyl groups on it were very nice heart imaging agents for a dog. And then the basis for the nuclear cardiology application of this chemistry is that if a person has had a heart attack or is at risk to suffer a heart attack, has some heart disease, then what happens is you look at the heart, and it doesn't become very well perfused with blood all the way around as it should in a normal healthy heart. And so if there's infarcted tissue, you see an image like this where part of the donut is not lighting up, and that means that part of the heart is not getting suffused with blood. And so this kind of diagnostic test is called myocardial perfusion imaging, because you're looking at how the heart is taking up blood in all of its different parts, because you can look at different angles of view, and one also tends to do this when the subject is at rest versus when the subject has been stressed. So you'll hear the term stress test associated with this type of image. And so this is really the first complex that Mike Abrams made that they were actually testing in animals. So here was an infarcted dog heart. You see, there's blood not getting to this part of the heart up here. And this image was to be compared with an image made using a different imaging agent, which was the state of the art at the time. Here, with just the first one, and there's so many choices you could make of what ligand to put on this metal, and the first one already works better than thallium-201 that's inserted just as an aqueous solution. Okay, so thallium-201 is also a popular isotope for applications in nuclear medicine. But with technetium now, you have the ability to make coordination compounds where the ligands are very tightly bonded to the metal center, and then you can attach other residues to this system by virtue of how you build the ligands. Okay, so that was really pretty amazing. And then a few years later, also in the research group of Alan Davison, professor of chemistry at MIT, comes along one James Frederick Carnegie, and what he decided to do for his thesis work was to go ahead and actually make molecules like the ones that Mike Abrams made, but to look at many different varieties with different peripheral substituents, because there are certain functional groups, organic functional groups, that will be metabolized and chopped up by enzymes in the body. These include ester groups, for example. You can also attach to these isocyanide ligands things that look like little proteins, and you can see then how those react to being injected. And so his goal here was really to make something practical that would be useful as a radiopharmaceutical for imaging organs. And as his discussion begins by just talking about the different groups that he was going to append to the surface of his coordination complex. And then here's a little synthesis slide from his thesis. Mike Abrams' thesis, the first one I showed you, was actually typed up by hand on a typewriter, but Jim Carnegie's thesis was prepared, he tells me, I was talking to him last night about this, using a very primitive word processor. Okay, one of the first generation word processors, but anyway, that's a little bit beside the point. You just don't see as many nice graphics in these theses as you do nowadays, but you do see a lot of beautiful chemistry. Here's an isocyanide ligand. Okay, look, we've talked a lot about carbon monoxide in this class as a ligand in its behavior to transition metals, and so if you just change the oxygen of carbon monoxide into a nitrogen, then you can have a substituent stuck to it. And so here's an example of an isocyanide ligand where the metal is going to attach to the carbon, and then Carnegie decided to put other groups out here. Here he's got a carboethoxy residue, and the idea was that enzymes called esterases in the body can clip off and metabolize the carboethoxy residue, and what that will do is it will affect the way that the technetium is biodistributed in the body, and so it will affect it'll affect the kinetics of how long the technetium takes to accumulate in an organ and how long it takes to then run out of that organ. Also he looked at examples that have organic amide functional groups, all connected to the isocyanide. So his thesis work was all about looking at different isocyanides, on 6 of them on technetium in the +1 oxidation state, so it's D6, low spin, octahedral, diamagnetic systems. Talks here about the radioactivity, talks a little bit about the technetium generator issue, mentions that he's doing a lot of this work in collaboration over at Harvard Medical School, so they had a lab over there where they were cleared to use 99M. The 99 work was done here at MIT. And this was because of the collaboration that I'll tell you about shortly. Okay, here's one that I won't bother to turn over, but this is actually a pretty important slide. You'll get this PDF file on the from our website, but you'll see that he's taking pertechnetate and saline, and these are the key feature here is that this synthesis is quantitative at these very low concentrations that are what are used for nuclear medicine. Now, I showed you that Mike Abrams imaged part of a dog, and as they progressed toward doing human studies, they also imaged the rabbit. And in these early tests, you have these chemistry PhD students, and they don't really know which organ is which in a bunny. So they had to get a diagram like this out, so they would have a map, so that when they start shooting these molecules into the bunny, they will know which organ they're seeing light up by the gamma camera. And this does not hurt the bunny. The bunny is anesthetized and doesn't know. This is a perfectly nice thing to do. And in this one, you'll see, I think the bunny is oriented this way. And here's the liver. And resting atop the liver on the diaphragm is the heart of the bunny right here. He's got a lot of different images. These in the digital thesis archive are a little bit fuzzy. So if you want to see better images, you might want to refer directly to the thesis. But you'll see that what he's doing here is he's looking as a function of time after injection, just the intensity of the gamma counts from the liver, from the kidney. Notice the heart starts out real high, and then it clears as the blood moves on into the kidney and the liver. And so you can actually take these images as a function of time and see where the technetium is going in this living bunny. And I thought I would mention that, but then thought I would also show you. Now this picture, I've seen this in the real hard copy thesis, and it looks much better in terms of organs lighting up and so forth. It's very fuzzy in this image from Carnegie's PhD thesis. And this, in fact, is Professor Alan Davison, who was himself the first test subject for his technetium radiopharmaceutical. He just couldn't wait to have this stuff shot into him so he could see what his organs look like when imaged with a gamma camera. So, I mean, that's Professor Davison, first human test subject on his own chemistry. And so that was pretty remarkable. And so let me tell you just a little bit more about Alan Davison. Okay, you can go and read about him at the MIT website, but this is Professor Davison. He's a colleague of mine in inorganic chemistry here at MIT. He became an emeritus faculty member this past summer, but his research career spanned 40 years here at MIT. He came in 1964, and he did research in a lot of different areas of inorganic chemistry and didn't get into technetium until 1980 because he struck up a collaboration with the fellow at Harvard Medical School, who I will show you next. But he's a Welshman. He got his PhD with the Nobel laureate Jeff Wilkinson at Imperial College London after Jeff Wilkinson was denied tenure by Harvard, and before, after which he got his Nobel Prize. So they didn't make a very good choice there. But in any event, Professor Davison learned and became one of the top inorganic and organometallic chemists of his generation. And in fact, he's now a fellow of the Royal Society, and which is quite a special distinction. I went over there for the ceremony in London when he was being inducted into the Royal Society, and they pull out the book that is signed by all the new inductees into the Royal Society, and one of the early signatures in the book is that of Isaac Newton. So he signed the same book as Isaac Newton. You have to make sure your hand does not tremble and blot the page. It would be a big problem. They actually go ahead and teach them how to sign the book, and they practice in advance because they use a quill pen dipped into ink, just the way Isaac Newton did it. And this coming spring, Professor Davison is going to Atlanta, as many of us chemists are, for the American Chemical Society meeting there. But he's going for a special reason, because he's winning the American Chemical Society Award for Creative Invention, which is a very prestigious award. And I believe he is the first from our department ever to win the award for creative invention. And that can go to a person in any area of chemistry, in fact. So that's a really nice thing. And Professor Davison was a great mentor of both undergraduate and graduate students here at MIT over the years. And next, let me show you that it takes not one Welshman, but two to make a drug. And here's the other one. Alan Jones, a very good personal friend of Alan Davison. He and Alan got together in the early 80s to see if they might not be able to bring inorganic chemistry and coordination chemistry to nuclear medicine in order to develop a diagnostic imaging agent. And they got together, and their research was extremely successful. And they have done research in other areas, too, together over the years. And their students go back and forth between the labs here in Building 6 at MIT and over at Harvard Medical School to do the different kinds of studies that they do. And so it turns out that this chemistry, making these 6 coordinate complexes of technetium-1, has led to the development of Cardiolite. And so it's called sestamib, and that's an abbreviation for this compound that has 6 of these isocyanide ligands on technetium. Okay, so now when you see sestamib, you'll know what molecule that is. It's actually the one that actually became commercial and was approved by the FDA in 1990 after extensive clinical trials was one. I'll show you the structure in a moment, but it's a variation on the tert-butyl where one of the methyl groups is replaced with a methoxy group. So it's a methyl ether species. And in this Cardiolite website, so Cardiolite was originally manufactured and brought into being by DuPont Merck, and they sold it later to, this is Bristol Myers Squibb, and so you'll see that Bristol Myers Squibb has a section devoted to medical imaging, and this drug that was the brainchild of Davison and Jones is currently the most widely used diagnostic imaging agent for looking at myocardial perfusion. So it's used in heart imaging tests all around the world every day. So it's a very important molecule contributing to the health and welfare of people all over the world. And what you'll see is there are here descriptions of the stress tests that people take. Let's see. Cardiolite imaging guide, you have education programs. Let's just check out the imaging guide for a moment. So these companies have pretty good graphics on their website. And so remember the donut I was showing you, there it is right here. So there are different ways to look at the heart using Cardiolite to see if the blood is perfusing the heart properly. I guess that might be the short axis. Okay, you can view the scan images. This is how a normal healthy heart will differ when it's been stressed after exercise or at rest. So that's why they call these stress tests. You're seeing how the blood is distributed in the heart using this property of the radionuclide technetium-99m. Okay, there's one. That's a different one. Okay, I'm not going to spend too much time on this, but I'm giving you the link to this website so you can go and look at how people actually use clinically technetium sestamib to image the heart. I want to show you just a few other things here. One of which is that, as you may be aware, the same molecule can have different names if it's used for different purposes. So Cardiolite is one of the names given to sestamib, but another name given to sestamib, here it is, sestamib, is miraluma. And miraluma, it turns out, is really quite useful at detecting breast cancer when breast lesions are not readily visible using mammography or ultrasound. And so you'll see, if you go to this website and look at the information for healthcare professionals, as you all are sitting here, you go in there and you'll be able to see breast tumors that are detected very nicely using sestamib that were missed using ultrasound or mammography. You might like this. If you try to go into that information, you're first confronted with a test, and you have to pass the test and know that the risk of breast cancer increases with age. So then it'll allow you, if you get that right, then you can go on and actually look at the images that are made using this drug. Okay. Now, I also give you a link here to the Cardiolite story. That is a nice article written in the MIT Undergraduate Research Journal about Professors Davison and Jones and their students and the creation of this clinical tool. So you can go there and read that, and it has some more information. And then finally, I do give you a link to Sestamibi. So you'll probably be appalled at the way this website draws the isocyanide complex of technetium. You know, we know very well that that's a linear bond angle at those carbon atoms, not bent like that. So that's not a very good representation in terms of structural fidelity. But if you want to know which isocyanide is used in vivo for imaging organs, it's this one with the methoxy group instead of one of the methyl groups of the T-butyl group. So it's very similar to the original one that Mike Abrams made back in 1983, because they already had T-butyl isocyanide around from other things. Okay, so it's a really remarkable story, fantastic story, and having told it to you, I'm now going to have to do something that I very much regret. Now you can go on and sample all the other exciting chemistry subjects at MIT in your future. I hope to interact with many of you again in that context, and I wish you good luck, and I know that you'll all do fantastic things. And having said that, I'm going to have to close the book on this semester.